So good afternoon to all of you, and today what we are going to, we have learnt about an operational amplifiers in the last lecture. Today what we are going to see is how to boost the gain. Okay, so some gain boosting techniques, and also we are going to see about the output amplifiers. So in the last few classes we never bothered about making the output resistance to close to zero, right? So if you don't do that, your final gain will be dependent on the load which we connect, right? So we don't want that to happen. So these are the two issues which we will take up in today's class, right? So how to boost the gain? Okay. So can you tell me what would be the gain of this first stage from what we have learned?
GMRD.
Yes.
Minus GMR.
Yeah, minus GMRD. Okay. What about this?
Sir, can you increase the pointer size?
It's increased, I guess.
It's coming very small.
Okay. What about the second one? Or the bottom one?
GM1 R1 R1 parallel R02.
Yeah, this is GM1 into R1 parallel to R02. What about this?
GMRD divided by 1 plus GMRS.
Okay. Just a simplified version?
RD by RS.
Yes, just
Minus
RD by
RD.
Okay.
Minus RD.
What about this? This is a cascode. Approximate one.
It's GM into R3 parallel with R2,
Yeah.
and again that multiplies with
Or
bottom.
because this as you look into the bottom, it is an high resistance. So I can say just a GM parallel to R03, right? Here in this
Yes.
case, if you see, it is a GM3 R03 R04. Okay. So this gets multiplied by GM R03 R04 GM. This is the approximate resistance as you see into the top here also. So if I write the gain equations, it is a GM RD parallel to R0 minus RD by RS. It is minus GM R01 parallel to R03. This is approximately a GM1 R03, and this is a this is a GM R03 R04. If I consider as now, if all of them are matched, it will become R0 square, and again multiplying with GM, so this will get a GM square, and half because you are looking onto the top and bottom, so they are in parallel. So this is this gain figures clear to all of you, right?
Yes, sir.
Okay. So now how to boost the gain? Okay, so boosting the gain is by putting now here the problem out here is there is 1, 2, 3, 4 transistors which are to be cascoded one above the other. Okay, so less of a headroom. Okay, so that is an issue. So your max swing available will be limited. Also your input common mode range, those things will get restricted. So instead of that, we can do these kind of arrangements. Okay, so you have an op amp, and then you put an NMOS out here. Okay, so the resistance as seen from here top, it gets multiplied, it gets enhanced a lot. Okay, so this is another configuration. So this is the equivalent circuit of this. Okay, so the thing is, by putting an op amp which is driving just an NMOS, okay, we can increase the output impedance, okay, without more cascode devices. Okay, so we'll see that how it is happening. So just consider this particular circuit. Okay, first. Okay, now what is being done out here? There is an RS which is put here. Okay, so the difference voltage out here, if this is the current which is going I out into RS, that is the voltage here. This is a V in, right? So the so the gate voltage for this particular transistor, okay, will be V in minus I out RS into A1. Okay, that is the gate voltage which is available here. Okay, and the source voltage is I out RS. So I write V minus of this. So I write minus of this. So here, if you see here in this particular equation from here, and the current can be a GM of M2. Okay, here when I say GM of M2 into this voltage, okay, I minus I out RS and this. So I out by V in will be, okay, if I rewrite this equation, it will be A1 G1 1 plus A1 plus G1 into RS. So this is the transconductance of this particular circuit. Is it okay? So let me explain you once more. The differential voltage out here is, here it is V in, here if you see here, it is minus I out VR. So this is a negative feedback which has been given. So I out is the current which is flowing into the into the circuit. So I out into RS. Okay. So now difference of these voltages is VD, which is available, and if the gain of this amplifier is A, so I multiply it by A. So that just gives the gate voltage. Now I have to find the gate to source voltage. So I am subtracting the source voltage. Source voltage is minus I out RS. Right, I out RS. So I am subtracting it becomes minus of I out RS. Okay. So I am subtracting the source voltage. So I am getting gate to source voltage. So this is the equation, right? So now that is I out VGS. Okay. Now that is the VGS of M2. Now if I have to find out I out, it will be GM. GM is nothing but GM of M2. So I get this equation. Now rearranging these terms, I get I out is equal to I out by V in, that is GM of this whole capital GM of this whole circuit to be A1 GM divided by 1 plus A1 GM RS. Okay. So this is one equation which we get, right? Now that is the total GM. Now if I have to find out the total resistance, okay, of this circuit R0, what has happened to R0. Now if you see here, I am applying a sample voltage here, and that's why this input I have grounded out here. So this current has got two components out here. Okay, one component is this, okay, that is Vx, okay, minus this Ix is flowing through Rs, so Vx minus Ix Rs by Ro. So that is the current which is going to flow here, right? Now there is an through R0. Okay, is this equation okay? This part is clear to all of you? Okay, so
this is to calculate I0, Vx minus Rs.
No, we have found out a capital GM. Now we are trying to find out R out, and for that we have put a sample voltage out here and trying to find out what is the current which is going to flow here.
Yeah. So in this equation, how you have written Ix?
Ix is this current which I have taken. Ix, which is when I apply a voltage, Ix, if Ix is the current, then I divide Vx by Ix, I will get the resistance as seen into this node, right?
Okay.
So that's why I put a sample test voltage Vx and test. So this is the current which is flowing. So this voltage will be Rs into Ix. So the voltage across R0 will be this, and what is the current which is going to flow here? It will be GM into, right, the VGS, and VGS in this case, this is ground, right? So VGS will be right RSIX here G, just the gate voltage will be A1 into, let me take a pen, right? This voltage will be Ix into Rs, right? This voltage will be A1 into Ix into Rs. So this voltage will be minus of that, right? A1 Rs Ix and RSIX. Okay, so this Ix has been taken common out here. So is it understood? And this is this is going to be minus GM. So this negative this current is flowing in this direction, right? So it is this is negative out here, right? This is ground, and hence this negative comes. Is it okay with all of you?
Yes, sir.
Okay, so this is actually A1 IX RS. So this IX has been taken out here for this voltage. This voltage is RS into IX. So this IX is again taken care of. And for the current you have to multiply with GM of this transistor. So that GM has been taken here. Now from this equation, if I do Vx by Ix, okay, I will get R0 out, right? So this is the equation for R0 out. Now if I have to find out the total gain, intrinsic gain of this, when I say intrinsic gain, it means that load is infinite. I am not looking about the load, I am just looking about the total gain which is available from this amplifier itself. I multiply these two. So if when I multiply these two, okay, if I neglect this part and this part, if I just assume this to be significant out here, and similarly if I neglect this one and consider this to be significant, okay, when I multiply this A1 plus G1, they will get cancelled out. One GM will get cancelled out. There is one GM in the numerator, so that will come here. This A1 will come here, okay. This RS and RS will get cancelled again, so R0 will remain. So this is the gain, okay, of this.
Yes. Why we should multiply R out
By
into
GM. That is the gain, right? Gain of an amplifier will be GM R0, right? So
GM
when we
R0.
take a complex circuit like this, we find the total transconductance and multiply it by the net R out. Okay, so that is the way we do. So when we do that gain, so you get this. Now if you see this gain, okay, it is like A1 times GM R0. Okay, so even the R out is very high and the gain is very high here. Okay, so you don't get these kind of gains by a simple cascading of two stages. Okay, so you don't get that kind of gain. So here you will find you don't have to put so many transistors one above the other and compromise on the headroom availability. So you can do these kind of things. Okay, so this is known as a gain boosting circuit. So I can implement that circuit. Okay, I can also have a cascode. Okay, this is a
Sir, one doubt.
Yeah.
Sir, how have you calculated this intrinsic gain?
Intrinsic gain is capital GM and capital R out.
Okay.
Okay,
So R out we got GM, capital GM.
this is capital GM.
Okay. This. Okay.
Right? So, right now you have something known as a regulated cascode. Okay, here the problem out here is it is like a CS amplifier where for high frequencies and from here to here there is a gain available, so it can affect your high frequencies. So you can have a cascode structure. Here also from here to here there is a gain available, right? So instead of that you can give a V in out here, right, and then you can put a transistor. So this becomes a common so when you look into here, it is a common gate amplifier, right? So from here to here there is no gain in this particular case. Okay, so that is why you will find Vp is approximately equal to V in, because GM into the resistance as seen here will be 1 by GM. So if you keep GM1 and GM2 almost the same, there is no gain. So this doesn't suffer from the issue of a Miller effect. Okay, so the same thing. If you try to find out the gain, you will reach around the same gain which is there. Okay, so the only thing is it doesn't affect have the issue of Miller effect, Miller capacitance out here. So that disadvantages is avoided by putting this transistor at the bottom out here rather than giving an input signal out here if you give it here. Okay, so this is known as the regulated cascode.
So M2,
Yeah.
M2 can have the Miller impact.
Here is it. Yes,
Right.
that can result in one transistor out here. But if you look into this op amp here, right, and then the input signal at each node, at this particular node, and you are looking into this amplifier. So from here to here, there will be a gain. Obviously, so this capacitance will come here, right?
Why we are shifting the above cap to below or intrinsic?
No. Actually, why we are here? Okay, the signal from here to here, but the small signal is I have no. Actually, what happens is okay, this signal, okay, this small signal, okay, this is if you replace it by a current source, okay, that gets the same current is going to flow here, because this current has got no other path. It has to flow out here, right? But whereas if you have a Miller capacitance here, your small signal will start getting shorted out here at this particular node itself, at the gate signal itself. You have a large capacitance. So this capacitance out here doesn't really affect your gain. Okay, when you are looking from here, it is just 1 by GM. So that doesn't come in the small signal path actually. Okay, so that is
Got it.
okay. Now,
Yeah, I just
tell me.
tried the sir. So it's boosting the gain. I just tried this. Whatever you said.
Okay, good. So you're
see
parallelly
the
doing
difference.
some simulation.
Yeah.
Okay, good. Okay. So this is known as an circuit implementation of this op amp. Okay, how to implement this op amp. Okay, so this is one way of doing it. Okay, so see, you have a V in going here, right? This has from here to here, and there has to be some amplification. So this is given into the gate of M3. This is a constant current source. So here to here. So what will be this G? Gain of what is A1? Can anybody say what would be A1?
GM3 R03.
GM3?
R03.
Yes, GM3 R03, if you are considering this as an ideal state. Okay, so if you see here, this is a small circuit only. Okay, so finally, okay, so this is the way we can implement the this could be the instead of just having an CS amplifier, so this kind of amplifiers can be made, which is using this gain boosting technique. Now, if I look from here to here, okay, the impedance will be 1 by GM. So there is no Miller effect out here. Okay, so this capacitance will come as it is. So at a high frequency also this can operate well. Okay, so this is one circuit. This also is same, right? Isn't it? What has been done? Instead of an NMOS, we have used a PMOS. We have given a signal here. This is the load which is connected in the bottom, and from here I have taken it to M2. Okay, this is the same circuit where we have used a PMOS stage for boosting the gain. Here also it will be GM3 into R03. Okay, this small G. So this is another.
Sir, in previous slide I have doubt.
Yeah.
Sir, how this feedback is happening here? That we are feeding VP from this gain boosting circuit to minus negative terminal.
Yes, this is just an amplifier, right?
But sir, the negative feedback is there, na?
Yes.
So in this right circuit, how it is happening?
Okay, so now an increase in V in, what will happen? What will happen here?
VP will drop.
VP will drop. What will happen here?
And then this will increase.
This will increase. So what will happen here?
This will drop.
Yeah, so it is like kind of an negative feedback only, right?
Yes, sir.
Correct? Right? More current
yes,
will
sir.
start flowing here, okay, through R0, right, of this transistor, right?
Yes, sir.
So this voltage will tend to increase. So this will try and maintain at the same level. Is it okay?
Yes, sir. Yes.
Sir, could you please
For a-
explain
yeah,
gain
yeah.
calculation of this circuit?
Okay, see, why is it a negative feedback? Just let's first be clear with that, then we'll talk about the gain. Okay, any increase in voltage out here. Suppose, let's assume this is say at around 0.5 volt. Let's just take any increase in voltage here, this will tend to fall to point, right? Because more current, which is going to, so this will tend to fall. If this is falling, current here will decrease, right? Right? If this will tend to decrease, so so this voltage will go high and more current will start flowing out here. If more current is flowing here through R0, right? So this capacitance, this voltage will tend to increase. So this forms kind of a negative feedback. Okay, and coming about the gain, right? This G, okay, A1 is nothing but G out here. It is GM3 into R03, because if you are considering this as an ideal op amp. Is it okay?
Oh, yes, yes. As per like last derivation.
Yeah.
Understood.
Yeah. Okay. Here also this is G. Okay. This is an folded cascode. Okay. Again, now if you don't want that this particular capacitance also to get affected, so you could have an cascode structure out here also. Here, like this is coming here to the gate, and this is an. This you remember, right? You did your assignment also. This is a folded cascode. You are giving an input to the PMOS. This is a load out here. That is being given to an NMOS here and a fixed bias here, and you are taking the output out here. Right? So you could further improve the frequency response out here. So these kind of circuits can be implemented, which has got higher gains than the traditional single stage amplifiers. Okay.
So, sir, I have one question. In the super transistor, this gate you are connecting to V in, right? V in, is it V in plus or V in minus?
This is single stage, so this is V. You can consider it.
Oh,
as
there is a
V plus.
separate. Okay,
Yeah.
this is a separate voltage.
Yes, this is separate.
But this point P that you are connecting to V in minus.
Which P here? This
This
is a
is from P.
differential amplifier, right?
Correct.
Yeah.
This is an op amp, right?
Huh.
A1 is an op amp.
Even is an op amp.
So,
But
yeah,
here,
so-
even it need not be an op amp also. It could be a single stage. It can be implemented like this also. Single stage with feedback, like it has been done here.
okay.
Okay.
But this P you are connecting back to the V in minus, the one of the
Correct.
inputs.
Correct.
And here you are giving a separate voltage. Okay.
This what is shown in the left has been implemented in the right by various structures by an
acha,
NMOS, right?
Okay.
So this op amp, instead of a differential amplifier, okay, I am using a feedback circuit here, right, where the output is through this again giving feedback. Okay, so that is here also this output is taken here, and a negative feedback is being given here. So here also same thing is happening.
Okay.
Okay.
So for folded cascode, how the gain will be?
Here it will be again GM3 into, see whatever, this is a current source, right? So this is the voltage which is being applied here, so it will be GM3 into that V in, so that same current will flow like this, right? So at this node we are taking the output, so whatever is the output resistance of M4 and I3, that this will just pass this is just passing this current to the top, small signal current to the top, right? So the gain will be the resistance of I3 in parallel to M4 and into GM3. Is it okay?
Okay. Yeah.
So now this is again folded cascode, a differential circuit. We were talking only about one part of the circuit. Now if you replicate that on the both the sides, and this is how it will look. Okay, folded cascode differential circuit. Okay, this bottom circuit we were talking about a single ended circuit. So we had this circuit. Okay, now the same circuit is it is like M1. Instead of M3, M4, I have M5, M7 here, a current source here. So this is one side of the circuit, right? Now this is the second side of the circuit, same thing. And I am giving a differential signal here. Now the differential signal will be applied out here, from here, and it will be applied to here. Obviously there will be some common mode voltage also needs to be applied. So this is the tail current out here. This is again the biasing current, and this has to come through these transistors. So this is how a differential gain boosting circuit, a differential amplifier with gain boosting signals can be made. Right? This is normal differential amplifier, two here, one here, and two currents. Instead of having a normal load, you have an this gain boosting circuit placed out here. So that is the only difference. So this is known as a folded cascode differential circuit. Okay, so you can implement these things in your LT Spice and see the results. Okay, how better it would be than your normal circuits. Okay, now in all these cases, okay, if I go back here. I am just talking about when I look from the top, okay, the resistance is much higher. Okay, now but after doing all these things, if you just put instead of this current source, if I put just a normal current source, the resistance as seen into the top will be much lesser, right? Then that will become a dominant thing. So whatever we have done in the bottom needs to be done in the top side also. Okay, only then you get a very high gain. Is it understood what I am saying here? Right? Final. Here we assume this as an ideal current source, but if you are going to just implement it with just by an PMOS and a constant bias, the resistance as seen into the top will be R0, right? And that is going to come in parallel with this. So all effort which we put in the bottom part to increase the gain, okay, so that will get destroyed by putting just a plane. So whatever we have done in the bottom needs to be replicated in the top part, in the load part. This is known as the signal path, and on the load path also you need to do that. So this is one proposed way of doing it here out here. Here the PMOS circuit is the signal path, and the NMOS is the load path. So this is the load path, right? And the same thing has been done out here in the load path to increase the resistance many folds, and it is done in the signal path out here. This is a cascode, right? So if you see here, V in is given here. It is here, and then you have a PMOS, and then you have a differential amplifier here. So this is a cascode gain boosting circuit. The PMOS network, and the load is with constant bias. Okay, there is no V in here because you are doing a constant current bias. So instead of just putting a constant current bias load, what we are doing is we are inserting one more amplifier here and two transistors out here. So this becomes super transistors out here. So instead of a normal load, we are putting in gain boosting has been applied to the load devices also out here. So this is how the overall structure looks like now, right? So this has got a much higher gain than a normal. So finally, if you want to make an circuit with very high gain, So this is the kind of circuit you should look forward. Okay. So this is a cascode structure. It is good for high frequencies, right? And this is high, very high gain as compared to almost you can get a gain of 200, 300 of that order instead of 10, 20 which you were getting initially in a simple structure. Okay, so that kind of gain can be achieved with these kind of circuits. Okay. Now coming to the load. Till now what we have been discussing was right, like the all these circuits, okay, had an issue of like if the final load has to be large, okay, but in an op amp, when we initially declared the specifications, we say that our final stage should be able to even drive the low loads. Okay, so finally the output resistance, so this is fine, okay, but ultimately at the end of it I should have some amplifier which can drive low loads also. So it should not be dependent on the load finally. Okay, so I have to insert one stage in the last. Okay, what will be that stage? Can anybody say? What?
Source follower.
Yeah, source follower is one of the options which we can have. Okay, so in many circuits, okay, in VLSI chips, we have the final transistors as BJTs instead of MOS transistors, because bipolar junction transistors they work, not only they do switch faster, but also they can have a higher current capacity per unit area. Okay, and that is, and hence the final stages. Okay, MOS devices, if you have to get good currents, okay, to finally to drive some loads which are connected off chip, okay, so low resistance and high capacitances, then you need to use a very large MOS devices, okay, with large area. Okay, so now if you see the construction wise, it is the MOS technology. So BJT is fabricated like this. You have an N-well out here, and then you have inside that you have a P-well, and then you have an emitter base, and this N-well becomes the collector. Okay, so how does an BJT works? So initially, if you don't give any base voltage to the base, you have an N and P and N, and then if you give an positive voltage to the collector, this PN junction will be reversed biased, and there will be no current which will be flowing. But when you give a small positive voltage to the base, electrons will be attracted from the emitter into the into this region. So the electrons will be available here. Okay, they'll come out into the P region, and since the structure is like this P well is surrounded all by N well, and so they will and you are applying a higher potential on the collector. So all these electrons will be, majority of them will be swept by the collector, and a small minority portion of the electrons which is emitted gets collected by the base. So that is why you have IE is equal to IB and plus IC, right? So essentially the collector current is a function of the base voltage you apply. So if you apply more base voltage, more electrons will be pulled from the emitter. A small portion of that will go to the base, but larger portion will come to the collector. Okay, because this is reverse biased, but because of this particular structure, the way it is built, okay, you have a P well surrounded by an N well, and you are giving a positive voltage at the N volt and with respect to the base, so the electrons are more likely to be pulled towards the collector. Okay, so that is known as BiCMOS technology. Okay, so that is done. Now, if you see the output stages, they are classified into a few: class A, class B, class AB, class C. Now, that depends on the conduction time of the transistors. Okay, if the transistor is conducting throughout the cycle, okay, in that case, it will be known as class A amplifier. But if the transistors are just conducting during a half portion of the cycle, Obviously there is some other transistor which will be conducting during this period. Okay. So depending on how the transistors are configured, so this is known as class B, where the transistors are conducting only during one half of the cycle, and in the rest half of the cycle some other transistor will be driving the load. Okay, so this is known as class B. We will see there is a great advantage of having a class B rather than class A. So class A is not generally used, class B will be used, or even better is class AB, where it is conducting for more than half period. Okay, so that means in this small region here, okay, both there will be two transistors will be simultaneously conducting. Okay, that is to avoid linearity issues, because when the current is very low here, if you have exactly at 180, there could be an issue during the crossover that the signal is not amplified. So if you have slightly more than 180, then that is an ideal case, and you could have, these are used in a very rare occasions where you have only portion of the signal being amplified, where it is conducting for less than 180. Okay, so these are the kind of four classes of amplifiers. Now if you see here, this is one amplifier. Okay, what is this? Is a normal common source amplifier. Okay, but it is capable of driving low load. Okay, why? Because the resistance as seen into this amplifier is very low. Okay, so we said R0 parallel to R01 parallel to R02, but we are ensuring that R01 and R02 is very low. Okay, so how is being done? By we know that R0 is 1 by lambda into D, assuming that obviously the same current is flowing out here. So it is lambda 1 plus lambda 2 into ID. Okay, they are in parallel, right? So this is the equation you get by keeping ID very large. Okay, by keeping ID very large, okay, I am able to make R0 out very low, and hence it is able to drive low loads also. Okay, obviously from here to here there won't be any gain, because all the gain which is required, voltage gain which is required, has to be done in the previous stage. Here there won't be any voltage gain, it will be only power gain out here. Okay, isn't it? Why will it be power gain here? Because there is a voltage here. Suppose there is a 1 volt here. Okay, the current here in the input side is almost negligible because it is the gate. So there is no power here. Whereas in the output, okay, the same voltage is available, almost same voltage is available out here, right? But large current can flow into the load resistance. So and hence there is a power gain. Okay, so so these are known as power amplifiers or output amplifiers. Is it okay with all of you till here?
Sir, when you say high load, that means low resistance?
Yeah, high load is low resistance. Okay.
Okay.
High load is low resistance, and when I said capacitance, high capacitance. Okay, low resistance. Okay. Now here now a few things which we need to remember out here is here now in this case, okay, this is a constant current source, right? When you look here, so here this can this current. So when I am pulling current from here, okay, this capacitor might have been charged, okay, fully. So this will be V out. So this has to pull this current, plus it has to take IQ also, right? So this current, okay, this particular I out minus I out is minus is maximum current which can be pulled out from this circuit, okay, will be K1 W1 2L VDD minus VTS square or minus an IQ, because this is the current, which can be given, right, by this M1 transistor, by this equation, right, because VDDS minus VTS minus VT1 square. Okay, that is the max current which can be pulled down for a max condition. Okay, in that max condition, this is the maximum current which it can pull down. Okay, but when this is pulling down the max current, this transistor also should be on. So this minus this current. So this is the maximum current which can be pulled from the load and from the load. Now, is it okay? Is this equation clear to all of you?
Sir, can you explain it again?
Yeah. See, so we are talking about the maximum. See, this is the load. Okay. We are talking about. Let me take a pointer. So the current will be like this, right? Okay. So the current which is flowing in this resistance. Okay. So this is the maximum current, and when it is negative means maximum current is being pulled like this from this load together. Okay. Maximum current will be pulled like this out here, right? So in that case, okay, so that current has to be this current plus this current together will be ID1. So this is ID1, right? That will be this I out minus plus IQ. So I put that IQ on the right hand side. So this has become minus IQ. Is that much okay?
Yes.
Now,
So, sir,
now how to
RL
size
value-
this transistor? How? Yeah, yeah. I'll come to you one
okay.
second, sir. So how to size this transistor now? Okay, for given that this is the maximum current, if that is the requirement, how to size this transistor? Okay, so this transistor can be I out minus IQ. Okay, first I can fix the value of R out depending on RL. It has to be close to less than RL. So that's why I fix ID. Okay, ID is nothing but IQ. So once that get fixed, okay, this is the maximum for this condition where maximum current flows out here. I will apply VDD here, right? That will be the condition. So this voltage will be VDD minus VSS, okay, minus VT1 square. So is this equation clear to all of you? These first two equations.
Sir, that ID with R out is IQ or ID1?
Which one? Here. This is
With
IQ,
R out,
right?
R out. No, with R out. In R out equation, that ID is IQ or ID1?
No, that is same. ID is IDQ in that case. ID is bias condition. We are not talking. The biasing condition will be the same current flowing from here to here. We are not considering the load in that case.
Okay.
Okay, and that R out should be okay. Then it should be less than RL. Okay, so that the gain is not dependent on RL. So whatever is the expected load, I will try to keep R out less than that. Obviously, the trade-off will be high power will be dissipated in this circuit. There will be no voltage gain from here to here, only power gain. Is it okay till here? Yeah, Syed,
Yes, sir.
you wanted, you had some doubt?
Sir, the CL,
Huh.
the CL in this case has to be should be larger or smaller.
No, we are talking like there could be large CL and a low RL load, and hence we are designing the circuit like this. Okay, okay. Now I out maximum. Okay, now I out maximum is when this is totally switched off. Okay, when the signal is going low. Here I am having this signal, right? So in that case, this entire current can go like this out here. This entire current can go off here, like this. In that condition, this will be the equation, right? I out is equal to, so it will be VDD minus VCG. This is the voltage which is given here to the, so this voltage. So now this, when this signal is this signal, the maximum voltage will be available here when this is almost in the edge of cutoff. So this is cutoff, the entire current can go here. So this is the equation. So by using these three equations, okay, we can design this particular amplifier. Is it okay? How to design this amplifier? right? First of all, RL will be known. Okay, what is the kind of load which I am expecting, right? For the kind of RL, I have to put R out, should be less than RL, say maybe 10 times lower than RL. So I fix ID, and once I fix ID, okay, this Kn will be known, okay, depending on the technology. So W by L can be set accordingly. Okay, is it okay? Similarly, the W by L of this can be set. So this is how we go about designing this amplifier. Is it okay with all of you?
Sir, how does that sizing impact the
So if you don't size it,
output?
okay, then we will not be able to pull that much current into this load. Right? When we want almost VDD to minus VDD swing here, and that particular at that particular loads, okay, whatever is given here, then those kind of currents will be required.
So, sir, that means which one should be larger size, M1 or M2?
No, both will be large. Both will be large. Okay, to satisfy these equations. If you don't size these transistors accordingly, then we will not be able to drive these loads. Okay, at those voltages.
And you said RL, CL should be less, right? RL
CL will be large, so we have to cater
CL
for that.
should be large, RL will be less.
Yes, that depends on the user requirement. So this amplifier has to cater for has to design for taking into large CL and low RL.
RL smaller means
here the current will increase. That much more power will be consumed in this circuit.
Okay, lesser resistance, right?
Yes.
Means RL is larger means
A load large means RL will be low. Okay, so current will be large.
okay, got it.
So Sayed, you can consider a loudspeaker whose input resistance is 8 ohm.
Yeah, 8 ohm.
Whatever.
Correct.
So that is bigger load.
Correct. Right.
Okay.
When you have a loudspeakers, it is 8 ohms, 4 ohms, right? 16 ohms of that range only. Right. So that can be considered. Okay.
Sir, one thing here, I out minus we are considering, but when the load will provide current, that will only flow through M1. It will not go to M2. Then why IQ is coming?
Because this cannot be switched off. This is a constant current source. So this
Okay.
M1 has to cater for that IQ current also.
Okay,
Right?
okay,
If
that's
it's
why
a
minus. Okay.
capacitive load, this will also provide current. This will also provide current at that
Okay.
point. So you have to take care of that.
Okay.
Okay. So this is the small signal equivalent. Okay. If you see an V out, it is these two resistance plus GL. Okay. GL is nothing but the load resistance. Okay. Now we have to target that we keep this much higher than this GDS. Okay. So that this is not dependent on the load. Okay. So that is one option. And it has got, there is a capacitance out here. Okay. Input side, right? If you see here, yeah, input side generally we put this capacitance out here. There is a coupling capacitance which is put here, right? No, this is C1 is CGD1 only. Okay. So that results in a 0, which will be given by GM1 into CGD1, and there is a pole also. So these three resistances, right? And then at this node, you will find CGD of this transistor, CGD of this transistor. Then there is one CL, and then and the body capacitor. So all those capacitors together, they form a pole along with these RDS1, RDS. So these are the pole, and this is one 0 which will be there in this circuit. So if I talk about the efficiency aspect, okay, now this is what we say, this is not very efficient. Okay, if you see here, okay, efficiency is given by the power which is given to the load divided by the power which is taken from the power supply. Okay, Now power to the load is V out. Okay. What is the RMS voltage? V peak divided by root 2. Correct. RMS is V peak.
Vm by root 2.
Yeah, Vm by root 2 or V peak by root 2. So V square by R will be the power, right? So this will be V out square, right? By root 2 will become 2 divided by RL. Okay. So V out square peak by RL. Is this okay? Power given to the load on the top, on the denominator, what is there, that is okay? Oh, so sorry, on
Yes,
the
sir.
numerator. Okay. What is the power going to the supply? Here we have given VDD, here we have given VSS. So VDD minus VSS. Okay. Suppose this is 15 volt, this is minus 15 volt, then it will become 30 volt. Okay. So this is VDD minus VG and IQ. Okay. That is a constant current. Okay. So that current will keep varying. Sometimes this current will go there or it will come bottom here. So but the average will be Q point will be IQ. Right. Now what is an IQ out here? We like we said here. Okay. This peak voltage is only VDD, right? So that will be VDD. Okay, suppose you can write it as VDD minus VS divided by 2 by RL. Okay, this IQ. Why have I written this? So suppose let's take a case where VDD this is equal. This can go maximum up to VDD, right? So this is the peak voltage. What is that peak voltage? VDD minus VSS by 2. Okay, this is the signal which is going here, right? So this can go from here to here, VDD to minus VDD. So if I take a difference of that by 2, okay, that is the average DC voltage divided by RL. So that is the average current which is flowing here. Is this okay? This?
For power supply current, like power supply, power, why we are considering load resistance?
Because here we have designed the IQ accordingly, right? So that this maximum current will flow in that this will be off, that IQ will flow here. Okay. So that is why that IQ we have when this is going here, this output voltage will be okay, maximum voltage out here, okay, peak voltage out here divided by RL. So that we have and that is the reason we are considering here like this in this equation. Where is it? Here like this. IQ as the current which is flowing in RL. We are sizing it accordingly. Is it okay?
So here our motive is to find how much power taken by load, like compared to power supplied by source.
Correct. Right. So if you see here, then these RLs they get cancelled. So I have VDD minus VSS and V2 peak square. Right. Now so consider V peak is half of VDD minus VSS, right? Because output is going to swing from VDD to minus VSS to VSS, right? So this is peak to peak. So this will be half of this, right? So the maximum efficiency which I get is only 25% in this particular circuit, because lot of time this current is just flowing from top to bottom here. So that is wastage actually, right? So it has got a poor efficiency. Is this okay with all of you?
Yes.
Okay. So now this is one example where Kn is given as 2 kp. This value is given. Vtn is given. Vtp is given. Design the W/L ratios of M1 and M2, so that the voltage swing of plus minus 1 volt is available at the output. It says okay. So this is the output voltage which I require. Okay. Slew rate is given out here, right? And if RL is given, CL is given, VDD and VDS, this is the problem statement, right? VDD and VSS is 2 volt mod of VSS. That means minus 2 volt will be given here in the bottom. right? L is given, CGD is given. Find the voltage gain and roots. Okay. Now, first of all, the peak current is 1 voltage, right? 1 volt divided by 1, because 1 to 1 peak I require. So 1 load resistance is given as RL. So I get this. Okay. Now the slew rate is also given. Okay. Now the slew rate is given CL into SR. Okay. This we did right initially also. Slew rate and capacitance is given, and from where I can find out the current, right? Is this equation okay? Slew rate into SR also will give this. Is the right? We did slew rate for the initial CS amplifier, right? So if you see here, this is so now if you don't have to take both of these currents into consideration. Okay, this and this. Only one of them, because both don't happen simultaneously. Okay, so when this voltage is maximum, that is the time current will flow, maximum current will be here, right? But this at that time, since it's already reached maximum, there is no current in the capacitor. Okay, but when is the maximum current in the capacitor going to flow? When this voltage is 0 and this voltage is switching from 0 to high. Okay, so that is the reason you have to take a bigger of these two values. In this particular example, both are same, so you can take I out to be 1000 microampere. If they are different, you have to take the bigger of that too. Otherwise, you can take in this particular example, both are same. Is it okay with all of you?
Sir, bigger of them, but we can supply this much current only. 1 volt by 1 kilo ohm, whatever we calculate here.
No, see, the current which is going to flow here is there, but if you have to meet the slew rate, suppose I have a larger capacitor, right, and if I have to meet the slew rate requirement, then this should be able to provide more current, right, into the capacitor. So this load is comprising of a CL and an RL. Right, so both I have to look after both the requirements. Is it okay?
Yes, sir.
Okay, so that is why I check both the requirements. Okay, CL and RL, and accordingly decide the value of the current. Okay, so the greater of the two currents should be taken, right? And then I have these are all straightforward equations which you just what we discussed here. Okay, which will give the sizing of the transistors. Okay. So I'll share these slides. I will request all of you to have a look at the values and the substitutions and how you have done, and also the gain. Okay, how they have got the gain, the 0 and the poles. Okay, so here we are assuming that the load capacitance is much higher. So straight away load and resistance they have multiplied out here. So just go through this numerical. So I have inserted this numerical. So that you have some kind of practice on design of this amplifier. Okay, it's a simple amplifier. Okay, so this can be done. Okay, now if you see here in this particular design, when the problem is when you should not have any current flowing into this resistance when the input is 0. That means when the input is 0, this biasing should be 0. Right, in this case that doesn't happen actually. It will be in a VDS plus. So you have there are certain circuits which are proposed out here. Here this is one case where you put an VDD by right 2 out. If you are putting it a ground here, this will be at VDD by 2. Right, so then some current can then you put if you don't want the biasing current to go towards the resistor, you can put a capacitor here. So this is one option available to us. The second option available to us is you are putting VDD and ground here. This will be VDD by 2 out here. Then on the other side of the resistance, you put 0.5 VDD. In that case also there will be no current flowing here. Only so you don't want that when the input is not there. Okay, you don't want any current flowing into this resistor. Okay, when the signal is going high, okay, the current can reduce because it is a negative and the other way around. Okay, so that can happen, but when the input is 0, essentially you don't want any current flowing here. So this is the second option which is available. or this is the third option, like we studied here. Here it is actually VDD and VSS, and if you try to keep this VDD and VSS, okay, in such a manner, and the sizing of this transistor that it is when V in is equal to 0, you get a 0 out here. So in that case also your load. So these are some of the techniques which are used, so that at when V in is equal to 0, no current is flowing to the RL. So these are the three options. Okay. Now we saw about class B operation, right? In class B operation, if you see here, this is also you are giving a voltage between the gate and the source. Here also you are giving. So both these transistors are actually working, right? Now when the signal is in the positive, okay, when the signal is positive, this is switched on, and you have biased it just above the threshold, so this will be switched off. Okay, so when it looks up, it will look like almost a high resistance. And similarly, when the signal is in the negative, this will be switched off, and when you look here, it will be high resistance. So this will be directly low, pushing current here, and similarly this will be pushing. So this is like both these transistors are working, right? So this is known as a class B operation, right? But at 0 volt, both of them will be switched off. So to avoid that, we are giving a threshold voltage here. Already we are giving a threshold voltage to this circuit. Okay, so you might be wondering why it is negative here, because this is VSS is like suppose this VSS is minus 15 and 1 volt is the threshold voltage, then this should be around minus 14 volt, right? So that it is just in the it is just about to be on, right? So that is the reason the negative is shown here, because you have a strong negative already out here. So you can do that, right? Now if you compute the efficiency of this particular circuit, if you try to compute the efficiency, again load is V out P. So the same voltage is being given to the load, so there is no problem with that. But what about the current which is drawn from the power supply? So it is like VDD minus VSS, that is the power supply, whereas the current is like a half wave rectifier. Only this current, this is providing this current into this circuit, and then it is switched off, and in the remaining part, this is totally switched off. Whatever is current is available in this network, that is being pulled down here. So I am not dissipating any power here. So this is only half wave. Now half wave rectifier, what is the average? It is V peak divided by pi, right? Pi, right? So V peak divided by pi. Okay, so that is, you can neglect these okay, it is just V peak by pi. So if you are, this 2 is already there, so this 2 is coming here. This is VDD minus VDS into that pi, because now we are talking only these transistors are on only during half 180 degree duration. Okay, so that is why it is like a half wave rectifier. So you put pi here, so this is a denominator, I have a pi here. So if you see here, this becomes, now in this case also max efficiency is when you are taking the peak value to VDD to VSS. Okay, so in that case V peak will be half of that, half of this. So the max efficiency now will come out to be around 78.5% if you see here in this particular case. So because you see constant current is not being dissipated in these two transistors. So this is another kind of amplifier. This is mostly used in the output stages. Okay, so finally these transistors can be replaced with BJTs also in many circuits, in today's VLSI circuits. When finally if I have to drive something off chip, either we use power MOSFETs. Okay, there are I think there is one chapter on power MOSFETs in Cedra Smith. If somebody is interested, you can have a look. Or we can use bipolar junction transistors also. Okay, so again class A, B, C, D, everything remains same. Okay, the kind of thing. Only thing is these transistors will be replaced with bipolar junction transistors like this. Okay, because fabrication of BJT also is possible in the CMOS technology. Obviously, they'll take more space and it is not suited for digital application, but in the analog domain, in the final stage, we do use BJTs. Okay, so that is known as BiCMOS technology. Even for the digital outputs, when we are driving in off chip, okay, something, right? In the final buffers, could be BiCMOS buffers, even for the digital circuits. Okay, so BiCMOS circuits will probably learn in the next semester. It will be something like this. You have an MOS, and then you will have an PMOS. Okay, you could have an bipolar transistor just in parallel to this CMOS also. Okay, you can have like that, or you could have a Darlington pair where one is MOSFET and the one is CMOS. This is the pull down network. Similarly, you could have the pull up network also, one Darlington pair, right? So BiCMOS technology is also used in the final stages. Okay. Otherwise, these two amplifiers, you should know. As far as this chapter is concerned, you should know the design of a Class A amplifier and the efficiency calculation, and also a Class B amplifier, its efficiency calculation. Okay. I think.
Sir, can you explain the operation of Class B again, like how it is half-wave rectifier?
Because see when the signal is going in the positive direction, right? This transistor is switched off because you have biased it in the threshold. So only this transistor is working, and it is going to pull down this node to 0, like a digital circuit. What is happening? There is no biasing current from the VDD to ground. Okay. Okay. Similarly, when the
during
negative cycle, this will be switched off, and only this will be switched on. So this is only going to work. Okay. So this is like an inverter now. Like, isn't it like an inverter? You are giving the input signal, right? But you are giving the threshold voltages also, so that in inverter we have that small region in between. Like initially, till it comes to VTN, this will not be switched on, right? But we are ensuring that even a small positive voltage, this will be switched on. Okay, by biasing it. And similarly, a small negative voltage, this will also be switched on. The top one, isn't it?
Oh, okay. Correct.
Now, if I make an small, if I just make an inverter out here, right? So till the time this goes to VTN, this will not be switched on. Okay. So I don't want that kind of loss of signal. Okay. I am giving a signal here. I am giving a negative voltage here. I am giving a positive voltage here. The moment this goes slightly positive, so this is already in the edge of the threshold. So I am giving the threshold voltage already here, so that even a small signal doesn't get lost because of the threshold. So this I am biasing it accordingly about the threshold voltage. Okay.
Yes, sir.
Okay. So we'll stop it here for today, and then in the next class, I think that will be the last class. We will talk about noise in amplifiers.